In this video, we will take matching pennies game and we will try to obtain Nash equilibrium in mixed action or mixed strategy. This is a matching penny game. We do probability allocation for player 2 here. We say that player 2 plays head with probability q and tail with probability 1 minus q. We can also say that player 1 plays head with probability p and tail with probability 1 minus p. For head, in short, I will use h, and for tail, t. This is what we will use. Of course, what is the requirement? That q has to be between 0 and 1 and p has to be between 0 and 1. That's the requirement. So now, if player 1 thinks that player 2 is playing head with probability q and tail with probability 1 minus q, what would be his expected payoff if he plays h? So 1 he will get with probability q and minus 1 he will get with probability 1 minus q. So from head we can write 1 multiplied by q plus minus 1 multiplied by 1 minus q, and if you solve it, it will come out to be 2q minus 1. Okay. Similarly, here you can calculate if player 1 plays tail, he gets minus 1 with probability q. So we can write minus 1 multiplied by q, and he will get 1 with probability 1 minus q. Because player 1 cannot individually decide in which box he is going to land. He can decide about row, but player 2 has to decide about column. So this is 1 multiplied by 1 minus q, and if you add it up, it's going to be 1 minus 2q. Okay, that's the way we can do. And similarly, given player 1 is playing head with probability p and tail with probability 1 minus p, we can check for player 1 expected payoff, player 2's expected payoff if player 2 plays head. So from head, we have to now pay attention to the second number because we are calculating payoff for the second player. This box, they will land up in this box with probability p. Remember, player 2 has decided to play head and player 1 is mixing between head and tail. So with probability p here, with probability 1 minus p here. So minus 1 this multiplied by p and 1 multiplied by 1 minus p. If you add it up, it's going to be 1 minus 2p. How about here? Same way we can calculate 1 happens with probability p, this, and this minus 1 with probability 1 minus p. So 1 multiplied by p plus minus 1 multiplied by 1 minus p, this is going to be 2p minus 1. So we have obtained the payoff. Now we can obtain the best response correspondence of player 1 given that player 2 is mixing with q. Of course, in detail we have to write that player 2 plays h with probability q and t with probability 1 minus q. So we can further write q multiplied by h. Of course, this is not multiplication, just to indicate, and 1 minus q with t. And this is q and 1 minus q. If we make sure that if we give just this, everything is described, and that's why I am writing here q. If we had 3 strategies, let us say if player 2 was playing left, middle, center, whatever the names are not important, better name would be left, center, right, and here is p, here is q, and this is 1 minus p minus q. Then of course, to describe these strategies we have to write p and q. By describing this p and q, because sum has to be 1 minus p, 1 minus, third one has to be 1 minus p minus q, because sum has to be equal to 1, and we can say the first probability is for L, second is probability for C, and third is for R. By writing p and q, we are able to describe it completely. So we are just writing BR1 as q. So what should player 1 do? player 1 should, playing h he gets 2q minus 1, by playing tail he gets 1 minus 2q. What should he do? So we can say if 2q minus 1 is greater than 1 minus 2q, he should play h. He should play h. Or in other word, 4q minus 2 greater than 0 or q greater than half, player 1 should play h. Similarly, if situation is reversed, if 1 minus 2q is greater than 2q minus 1, this is coming from playing t and this is coming from playing h, then he should play t, just because t is giving him more, and this translates into that q less than half, player 1 sort p1 plays t. And there is a third possibility. What if 4q minus 2 is equal to, or sorry, 2q minus 1 is equal to 1 minus 2q, or q is equal to half, then p1 is indifferent between playing h or t. We can write it that best response correspondence of player 1 when player 2 is playing q is equal to h if q happens to be greater than half. P2 plays h with q and t with 1 minus q. That's what we have. Is t, and to be, because it is correspondence, if q is less than half, and is both h and t if q is equal to half. Here we are writing in probability term, here we are writing in the action term. So this can also be written, because we also talk about player 1 plays head with probability p. So what it means is, basically, let me use a different color, it means that p is equal to 1. That's what playing h means. And this is p is equal to 0, because t he is playing with probability 1 minus p. So if p is 0, the probability here is 1. So that we can write. And this is that p can be anything, it can be 0, it can be 1, it can be half, because if h and t both are best responses, then we can say any combination of h and t would also be a best response, and that we can check. Let us say here we have h t 1 minus 1 1 minus 1 minus 1 1 minus 1 1. This is with probability half and half, and player 1 is playing h with, let us say, 1 by 4 and t with 3 by 4. What is going to happen? We can calculate that what is the probability they will end up in this box. The thing that we have to assume, that probability distribution here and here are independent. These two players are not coordinating. There is no other parameter that helps them coordinate. They are deciding on their own. So this box will happen with probability 1 by 2 coming from here multiplied by 1 by 4, and player 1 is going to get 1. Further, from this box, it happens with probability half multiplied by 1 by 4 multiplied by minus 1. This box happens with probability half multiplied by 3 by 4 multiplied by minus 1, and this box happens with probability half coming from here and coming from here 3 by 4 multiplied by 1, and this is what we have to obtain. So this is 1 by 8, this is minus 1 by 8, this is 3 by 8, but there is a minus sign, so minus 3 by 8, and plus 3 by 8, it gets cancelled. So we see that, the payoff comes out to be 0. I want to make a further claim that, of course, here we have obtained for a special p that p is equal to 1 by 4 and 1 minus p is 3 by 4. In fact, if we take any p, the payoff is going to be equal to 0, and let us do that quickly. 1 minus 1 minus 1 1 minus 1 1 1 minus 1 h t h t. This player 2 is playing with probability half half, and player 1 here p and 1 minus p. So the payoff to player 1 would be here if player 1 is mixing using h and t with probability p and 1 minus p. This box is going to happen with probability p divided by 2, because half is coming from here, p is coming from here, and the gain is 1. This box is happening, minus 1 is happening with probability p and half here. So you see this term gets cancelled by this term, but we will have two more terms. This box is happening with probability half multiplied by 1 minus p coming from here, and this box is happening with probability half multiplied by 1 minus p. So half multiplied by 1 minus p is common. Here is plus 1, here is minus 1. This will cancel and it will get you 0. So it doesn't matter how player 1 is mixing, the payoff is always going to be equal to 0, and therefore we allow for all p. And similarly, we can write the best response for player 2. How can we write the best response of player 2? Player 2, we have obtained that given player 1 is mixing, given player 1 is mixing between h and t with probability t p and 1 minus p respectively, player 2 gets this if she plays h. We have to see the number. What is that? She gets 1 minus 2p. 1 minus 2p, and 2p minus 1 if she plays t. So I have repeated this exactly same thing, and so clearly what would she do? She will play h if 1 minus 2p is greater than 2 minus p, or 2 is greater than 4p, or p is less than half. P2 should play h. If p greater than half, and I am getting here faster by changing the order, you can do, P2 should play t, and p is equal to half, P2 should play h or t or any combination of h and t. So in different way, how can we write? If we want to use best response of player 2 given player 1 is playing p, is player, if p less than half, player 2 should play h. Playing h means this q has to be equal to 1, and 1 minus q has to be equal to 0. So both will be satisfied when q is equal to 1. So player 2 should play q is equal to 1. If p is greater than half, q is equal to 0, and if p is equal to half, q could be any number between 1 and 2. And that's how we get best response correspondence for player 2, and here best response correspondence for player 1. So we have obtained best response correspondence for both the players. And as we know, best response correspondence is the first step towards obtaining the Nash equilibrium. So in the next page, I have already written best response correspondence of both the player, and we will try to obtain the Nash equilibrium. Just to remind you, P star comma Q star is a Nash equilibrium if P star happens to be one of the best responses coming from player 1 given player 2 is playing Q star. Also, that Q star happens to be one of the best responses coming from player 2 when player 1 is playing P star. It's exactly the same. The only difference is that now in place of pure action, we are also allowing for mixed action. So that's it. So the first take is that start with some P star Q star and check whether they indeed are best responses of one another. If we find they are best responses of one another, we have obtained our at least one of the Nash equilibrium. So let us start with half comma 3 by 4 just to check. If player 1 is playing half, then what is the best response from player 2? Player 2 has infinite number of best responses. Everything between 0 and 1 would constitute a best response. And if everything is a best response, then 3 by 4 is also in the list of those best responses. So clearly player 2 is playing his best response given what player 1 is doing. We have to look at other way around. Player 2 is playing 3 by 4. What is the best response from player 1? We are in this zone. Here Q is greater than half, 3 by 4 is greater than half. The best response from player 1 is to play P equal to 1. Half is not equal to 1. Therefore, player 1 is not playing his best response, and therefore 1 by 2 comma 3 by 4 cannot be one of the Nash equilibrium. Now, can we propose something else? Let us check half comma half. So we have already figured out that if player 1 plays half, the best response from player 2 is to play any Q. And any Q is allowed, then half is also allowed. So half is definitely one of the best responses. That is done. If player 2 is playing half, what would be the best response from player 1? Anything between 0 and 1. Half also is there, and therefore this half is also one of the best responses of player 2 playing half. So we can say player 1 is playing one of his best responses given what player 2 is doing, and player 2 is playing one of her best responses given what player 1 is doing, and therefore it is a Nash equilibrium. What does it mean? That will have to wait some time. Right now we are concentrating on obtaining Nash equilibrium. But there is too much of randomness in this technique. We have to think, propose and check. Is there any better way? I don't know whether it is a better way or not, but definitely this way that I'm going to talk about now is going to be helpful. So let us start with player 1. Let us say player 1 plays P is equal to 0. Another way this technique that I am going to talk about is useful, that it will give us the list of all Nash equilibrium, while this will only help us check whether a proposed candidate is Nash equilibrium or not. So if P is equal to 0, player 1 is playing only T, what would be the best response from player 2? Coming from here, Q equal to 1 is the best response. And if player 2 is playing Q equal to 1 means head, then what is the best response from player 2? Player 1, that is also 1, that is to play head. So what is happening? We are starting at P equal to 0 and we reach to P equal to 1. So we can be certain that this is not a Nash equilibrium. Why? Let us pay attention to this. If P star Q star is a Nash equilibrium, Q star is a best response of one of the best response of P star. So that's what we will get here. And if indeed P star is also a best response of Q star, we are able to come back to the same point where we have started. So that's what we are trying to do here. We are trying to complete the loop. So P equal to 0 that we have started. Next step is that P between 0 and half. If P between 0 and half, that gives us Q equal to 1, and if Q equal to 1, that gives us P equal to 1. So this is also not Nash equilibrium. We cannot have a Nash equilibrium in which P is between 0 and half. Now let us come to P equal to half. If P equal to half, all Q's are possible. Okay, and that gives us all the possibility. P equal to 1 when Q is greater than half, P equal to 0 comma 1 when Q is equal to half, and P is equal to 0 if Q is less than half. So we have started with P is equal to half. Our aim is to come back to P equal to half. This will not bring us P equal to half because that is giving us P equal to 1. This will also not get us to P equal to half because it is bringing us to P equal to 0. This can give us P equal to half because that's a possibility here. So one can start with P equal to half. If one takes Q also equal to half, you get back to P equal to half, and therefore half comma half is a Nash equilibrium. Now you can take P greater than half. We can constitute everything here. Why unnecessarily increase the step? If P greater than half, you get Q is equal to 0, and Q equal to 0 will bring you to P equal to 0. Again, loop will not complete, and therefore you cannot have a Nash equilibrium in which P greater than half means player 1 is mixing using probability P that is greater than half for H, and 1 minus P that is less than half for T, and that cannot be a Nash equilibrium. So we checked here in this technique, we checked that there is only one Nash equilibrium in which player 1 mixes with probability half for H, probability half for T, player 2 mixes with probability half for H and half for T. And that's how we are able to obtain Nash equilibrium. But this is again very messy. In two-player case, we have distinct advantage. So let us draw the graph. On x-axis, we can plot P. On y-axis, we can plot Q. And let us say it could be, half 1. Here is again, this is not to the scale, and there is 1. So let us first do what would be the best response here. Let us obtain here for player 2 in blue color. If P is less than half, this should be, this is, if P is less than half, it means we are in this zone. This zone we are. If P is less than half, then Q is equal to 1. So in this, for each value of P between 0 and half, Q happens to be equal to 1. When P is equal to half, Q are, everything is possible. So this is the way. And that's why we are calling correspondence. For P is equal to half, infinite number of possibilities are there. And if P happens to be greater than 1, Q is equal to 0. So this is the way we get. Let us use orange color for player 2. If Q is equal to half, all P are possible. So this is all P. If Q is greater than half, in this zone Q is greater than half, P is equal to 1. So this is the way we get. And if Q is less than half, P is 0. So on y-axis, P is equal to 0. So this is a point where best response correspondence, they overlap, and this point is half comma half. So clearly this is the Nash equilibrium for the game. Okay, that we have already discussed, that why do we get the Nash equilibrium on the point where best response correspondence would overlap one another. So this is the way you would obtain mixed strategy Nash equilibrium. I'm going to do one more example and then we will do one application and then we will try to understand what do we mean by mixed strategy Nash equilibrium.